Hello, we continue with parametric equations and today we shall discuss arc length. Let me remind you the formula for distance between 2 points in the plane, the length of the segment between 2 points. So if we have a point A with coordinates A1, A2, and a point B with coordinates B1, B2, the length of the segment from A to B, we can call it this way, and this will be square root A1 minus B1 squared plus A2 minus B2 squared. So let's say we have 2 points A and B, and this way we can compute analytically the distance between them. Now what about the length of a curve? Suppose we have a curve that starts at point A and goes to point B, and the curve has equations x equals xt, y equals y of t. T is a parameter that changes from A to B between these two values. So A will be the beginning of the curve. This will have coordinates x of A, y of A, and B, the point B has coordinates x, B, y of B. The curve can be approximated by small segments, and the length of the curve will be approximated by the sum of these segments. When the number of segments increases to infinity, we come into this formula, arc length formula. S will stay for the arc length. This will be integral from A to B, square root dx dt squared plus dy dt squared dt, integral that depends on t. Very often these integrals are very difficult to compute. We shall see some examples where this will be possible. Here I want to remind you the case with the Cartesian coordinates. Suppose we have function of one variable fx, and we want to find the arc length for the graph. Let's say x goes from A to B, and we have graph of the function like that. At the beginning we have the beginning point is A f of A, and the end point is B f of B. We can think of this like parametric curve where x equals x itself and y equals f of x. X going between A and B. So instead of t, we can write just x here. Arc length then will be integral from A to B, square root x prime is just 1, here 1, plus y prime is f prime x, this thing squared dx. This formula you have seen before when you studied applications of integrals. Now we can do some examples. I will start with one example which seems very simple, but it very well demonstrates the situation with arc length. So in our first example, I shall use a Cartesian equation. Let's say we take a simple parabola y equals x squared, where x changes between 0 and 1. Here is a simple picture. Suppose this is the coordinate system. Here is 0, x-axis, y-axis. Parabola y equals x squared will look like this. And here we shall take this part from 0 to 1. So we want to find arc length. Let's make this red arc length of this part of the parabola. How long is this parabola? Suppose you can stretch it and measure it. What will be the length? Okay, our formula for arc length will give you integral from 0 to 1 square root 1 plus f prime is 2x squared dx. So this will be integral from 0 to 1 square root 1 plus 4x squared dx. Now, it will be good practice to compute this integral. We have seen such before. And we can do the integral two ways, either using trigonometric substitution or even using hyperbolic substitution. Or we can do the integral by parts. I want to review this technique of integration and evaluate this integral by using integration by parts. Here the formula is this: if you have u dv, you get uv minus integral v du, and you put limits when necessary. Now I shall take u to be this radical 1 plus 4x squared, and v will be just x. So we have here actually u dv. Applying the formula, we have the product uv, and I shall put v first, x first, square root 1 plus 4x squared between 0 and 1, minus integral 0, 1 v du. So I have to put here x and the derivative of u. What will be the derivative? We can think of u like 1 plus 4x squared power 1/2 and differentiate by the power rule. So this will be 1/2 in front. 1 plus 4x squared negative 1/2, so this goes in the denominator, and then times the derivative 1 plus 4x squared, which will be 8x. I shall put here 8x, and in the denominator we have 1 plus 4x squared and then dx. Okay. Continuing this work, we can compute the integrated term between 0 and 1. At 1 we have root of 5, just this. At 0 this is 0. Minus integral 0, 1. We have here inside the x with x will give you x squared. A divided by 2 is 4. There will be 4x squared on top over square root 1 plus 4x squared dx. Okay, now I shall modify this integral and bring it to our initial integral, the arc length integral. How can we do this? We can add and subtract 1 plus 1 minus 1 here to the top, and this will be root of 5 minus integral 0, 1 4x squared plus 1 over square root 1 plus 4x squared dx. So we split in two integrals, and then plus minus minus gives you plus integral 0, 1, just 1 on the top, here denominator 1 plus 4x squared dx. Okay, In the second position, we have our initial integral, because we can write 4x squared plus 1 like root of 1 plus 4x squared squared, and reducing by this radical, this will give you exactly our initial integral. So this will be square root of 5 minus s plus, let's modify the second integral. Here in the second integral, we can make a substitution x to be 1/2 t to remove the 4, the coefficient 4. So this will become integral as 0 goes to 0. When x is 1, t is 2. 1 over square root 1 plus t squared. The x equals 1/2 dt, here 1/2 in front, dt. Very good. This integral that appears have been mentioned before. It's a table integral, and we have, let's make root of 5 here much better. Root of 5, repeating root of 5, minus s plus 1/2. This integral is natural log t plus square root 1 plus t squared. We don't need absolute value, this is positive, between 0 and 2. Evaluating, this is square root of 5 minus s plus 1/2. At 2, we have 2 plus square root of 5. At 0, this will be 0, because there will be 0 in the place of t, then the radical will be 1, logarithm 1 is 0. So 1/2 natural log 2 plus root of 5. Interesting. And remember, all this is s, so we can solve for s. If we bring this s to the left, it becomes 2s. And solving for s, we have 1/2 root of 5, and here plus 1/2 this logarithm, 2 plus root of 5. Look, this is our arc length, with some practice on integration by parts. Okay, moving further. Now let's do parametric equations. Example 2. A very simple popular curve is the circle. Let's see how our arc length formula works for the circle in parametric equations. So we take a circle with radius r like that, centered at the origin. It has parametric representation x equals r cosine theta, y equals r sine theta, and we're changing theta between 0 and 2 pi, one complete tracing the circle once. And let's see how the formula will give. It's good to compute x prime squared, y prime squared separately according to the variable theta. Differentiating, we have x prime is negative r sine theta, y prime will be r cosine theta. Okay, x prime squared plus y prime squared will be r squared sine squared theta plus r squared cosine squared theta. Factoring r squared, inside we have sine squared theta plus cosine squared theta, which is 1. So all this is r squared. And here we can write the arc length from 0 to 2 pi. Square root just r squared here, d theta. Root of r squared just r, let's put it in front. We have 0, 2 pi, integrating 1 d theta. This is r theta, evaluated between 0 and 2 pi, and this is, of course, 2 pi r the familiar formula for the length of the circle, circumference. This is it. Works very easy, very simple. We can move to ellipse. Let's take this ellipse. X squared over a squared plus y squared over b squared equals 1. This is the way a standard equation of ellipse centered at the origin. One axis is A, another axis is B. So it looks like that. Here is A, here is B. On the other side, negative A. We have such ellipse, more or less like that. Parametric representation is x equals A cosine theta, y equals B sine theta. Because we want to talk about the real ellipse, we did the circle already, we assume that A is different from B. Otherwise you have our circle. In the parametric representation, for one complete tracing, we have theta between 0 and 2 pi. Okay, what happens now to the arc length? S will be 0 to pi, square root, x prime will be negative A sine theta, all this squared, plus B cosine theta. Let's make this better. Okay, all this squared d theta. And we can write it also this way. 0 to pi, square root A squared sine squared theta plus B squared cosine squared theta, d theta. Now, it's useless to try to simplify this and evaluate like we did with the circle. This integral is difficult, I would say non-solvable. It has a special name, it's called elliptic integral. Elliptic integral. Elliptic because it shows the arc length of the ellipse, and when A is different from B, integral simply cannot be evaluated explicitly. Good. Moving to another example. Now we shall do real parametric equations. So this is example, ellipse was example 3, we're going to example 4. And here we have these two parametric equations. X is et minus t, y is 4 times exponential t over 2. And t will change between 0 and 2. We want to find arc length, so we compute separately the derivatives. X prime will be et minus 1. Y prime will be 4 times, here comes 1/2 exponential t over 2. So this will be 2 times exponential t over 2. Computing separately x prime squared plus y prime squared. Et minus 1 squared plus y prime squared will be 4 exponential t, just this. And here we work the square, it will be first squared minus 2 times the product, so this will be 2 times et plus second squared and plus 4 et. We can put like terms together. These are like terms, and this becomes exponential 2t plus 2 times et plus 1. And this is easy to see. This is a perfect square. et plus 1, all this squared. Okay, so everything becomes very easy. Square root x prime squared plus y prime squared is square root et plus 1, all this squared. So the square root disappears. This is just et plus 1. And the arc length will be integral from 0 to 2, et plus 1 dt. Very simple. We integrate et plus t between 0 and 2. So this is e squared, e second power, plus 2, and then minus value at 0, 1, and t at 0 is 0. So that's it. E squared plus 1, the arc length. Very good. And here comes our last example. It's number 5, okay? Yeah, number 5. Look at this curve, parametric curve. X equals t power 3/2, y equals 6t. And t is changing between 0 and 1. Find arc length. Again, it's always good to compute x prime squared plus y prime squared separately. Here we have x prime 3/2 t, 3/2 minus 1 is 1/2. Y prime is 6. Okay, x prime squared plus y prime squared, this will be 9/4 just t plus 36. And we can even simplify this, right common denominator. This will, because you have to take square root, this will make things easier. 9t plus 4 times 36. 4 times 30 is 120. 4 times 6 is 24. So this is 1 plus 144 over 4. And arc length now, the formula is 0, 1. Square root of this thing, 9t plus 144 over 4 dt. We can distribute the square root top and bottom, and the root of 4 is 1/2, will be 2, so 1/2 comes out. And here I'm writing the integral. Okay. This becomes very easy if we break the radical in two parts. We have exact squares here. 9t plus 144. It'll be very easy to write it this way. 144, and then this will be 3t 1/2 plus 12. Okay, if you feel nervous about this, you have good reason. This is not correct. You cannot do such things. You cannot break radicals like that. Don't do that. If you have square root a squared plus b squared, this is not square root a squared plus square root of b squared, which will be a plus b. It's very easy to understand that this is not correct. If you put 1 in the place of a and b. Square root 1 plus 1 is different from square root of 1 plus square root of 1, which is 2. And on the left side you have root of 2. So obviously these are two different things. Okay, just to show you a typical mistake that happens sometimes, don't cut the radical like that. Continuing this work, here again, our arclength, this is 1/2, 0, 1, square root 90 plus 144 dt. To solve this integral, we make a simple substitution. U is 90 plus 144. du is 9 dt. Dt is 1/9 du. And we have 1/2 in front, 1/9. This will be 1/18. How the limits will change, let's see. When t is 0, here we have 144. When t is 1, we have 153. Root of u du. Root of u, this is u 1/2, so we can integrate and write 1/18. By the power rule, u adding 1 becomes 3/2 multiplied by 2/3, divided by 3/2 actually, and between 144, 153. Okay, we have 1/18 times 2/3. This will be 1/27. And we have 153 to power 3/2 minus 144 power 3/2. Well, now you can simplify 144 power 3/2 because you can take first 1/2 power, which is 12, then cube. That's not so important. Okay, so we have this example. You see that computing arclength involves sometimes interesting integration, and sometimes integrals cannot be solved, like with the elliptic integral. Enough for now. Goodbye.